Okay, Bismillah ar-Rahman ar-Rahim. We have seen in the previous class the MSSP module. This MSSP module can work as SPI and it can work as I2C. Okay, so the same module can work as SPI and I2C, and we have the registers with the control and the configuration register. We can select between the SPI mode and the I2C mode. So SPI is for serial peripheral interface, and the I2C is for inter-integrated circuit, so IIC or I2C. We have seen that we can use the synchronous port if we want to connect two devices serially, okay? And these two devices can be at the same area or close each to other so that the master can generate the clock signal to the slave. Okay, so the two devices, they will share the same clock signal. So the module that is responsible for this is the MSSP module, okay? So we have seen, we have three registers for the configuration. We have the SSP status, and we have the SSP control 1 and SSP control 2. For the SPI mode, we need the SSP status and SSP control 1. And for the I2C, we need SSP status, SSP control 1, and SSP control 2. So this is how to connect two devices by using the SPI module. We have seen this previously. So we have the serial data output of the master. So here we have the master, and here we have the slave. So the serial data output should be connected to the serial data input of the slave, and the serial data output of the slave should be connected to the serial data input. And you can see that the master has to generate the clock signal. So the clock signal is an output for the master and is an input for the slave. The master also has to generate the chip select pin. So the chip select pin can be any pin of the PIC microcontroller. It can be any pin from any port, okay? It can be A0, A1, A3, etc. Okay? And you have the chip select pin. So here the chip select pin, so you have SS bar. So if you want to select one device, so this bit will be 0. If you want to select this slave, for example, this bit should be 0. If you have only one slave, we can remove this line, we can connect this to the ground so that this slave will be always selected. Or we can use the chip select from the master, connect to the slave select of the slave. So if you want to initiate the transfer, first of all, you have to put this bit as 0. If you want to start sending something, you have to select the slave. So we have to make the chip select as 0, send the data, and once you have done, we have to return back to the high state. This is for the chip select. Any question about this?
No, clear.
Okay, so I've seen how to connect multiple slaves. So I've seen two techniques. The first one is to use multiple chip selects. Chip select 0 is connected to the slave 1. Chip select 1 is connected to the next slave, etc. So we have seen that if you want to reduce the number of chip select pin, we can use a decoder. Okay, so we can use a decoder, for example, 3 to 8. So if we use this decoder, we will be able to connect 8 slaves by using 3 chip select. If you have more, we can use 4 to 16 decoder, etc. And you can see that the clock is connected to all the slaves. The serial data output of the master is connected to all the serial data input of the slaves. And the serial data input of the master is connected to all the serial data output of the slaves. So this is the first technique. So we have seen the second technique, which is the daisy chaining. So the daisy chaining, how does it work? So we have the serial data output of the master will be connected to the data input of the first slave. And you will get out of the first slave and you will go to the second slave. From the second slave, we will go to the third slave, etc. So this technique is called daisy chaining technique. And the clock is the same for all the devices. So what is the disadvantage of this technique?
When one shut down, the system shut down.
Okay, so if one of the slaves shut down, we'll lose the connection of all the slaves. The second disadvantage is that this technique needs to swift or to shift the data from one slave to another slave. So it is complex in terms of programming, okay? For the mode, we have seen that we have 4 modes of the SPI, and these are related to the clock. We have 4 clock modes. We have seen previously the 4 clock modes. This is the table. So these are the 4 modes of the SPI. And you have 2 bits to select one of these modes. We have the CKP bit and the CKE bit. So according to the values of these 2 bits, we can select the mode. So these are the 4 clock modes. So here we have write to the SSP buffer. So we can write at this low to high edge, or we can write at this high to low edge, or we can write at this high to low, or this low to high edge. So these are the 4 clock modes. And why do we have 4 clock modes? Because we have different manufacturer of serial devices. So each manufacturer has its own protocol. So if you have 4 modes, that means you can connect any SPI device to our PIC microcontroller. And also for reading the data, for sampling the data, we have the SMP bit. So if it is 0, the sampling will be at the middle of the data. If the SMP is 1, the sampling will be at the end of the data. So these are all the configurations that you have, so that if you want to connect any SPI device, you have to check from the data sheet the clock mode and the sampling time. And according to the data sheet, you have to make the configuration of the SMP bits, and you have to make the configuration of these 2 bits, the CKP and the CKE. We return back to the table. So here we have the values of the CKP and CKE bit. So if the CKP is 0, CKE is 1, this is called mode 00. If the CKP is 0, CKE is 0, this is called the mode 01, etc. 11, it is called the mode 10, and 10, it is called the mode 11. So the CKE is 1 bit of the SSP status, whereas the CKP is 1 bit of the SSP control 1 register. So for the configuration, we have the SSP control 1 and SSP status for the SPI mode. For the I2C, we know we need also the SSP control 2. So from the SSP status register, we have seen that we need the SMP bit, the CKE bit. And we have also need the buffer. So the buffer will give us the states of the communication. So this is the buffer. So if the buffer is 0, that means the receive not complete. That means the SSP buffer is empty. There is a Shaba, please, one minute, please. Can you hear me?
Yes, Doctor.
Okay, so if the buffer is 0, that means the receive didn't complete. That means the SSP buffer is empty. When the receive or the transmission is completed, the SSP buffer will be full. That means the flag will be 1. So same as the TX and the RC. Okay, so if the flag is 1, that means there is a data ready to be read. Okay, so the buffer is set when the SSP buffer needs to be read. And once you read the data, the buffer will be cleared automatically. When the SSP buffer is read, the buffer is cleared automatically by the peak. Now, if the buffer is set, that means there is the data that needs to be read. And the SSP buffer register is not read before another byte is exchanged. So this will make an overflow. And there is a bit, or there is a flag to detect this overflow, which is the SSP OV, SSP overflow. So if the SSP OV from the SSP control register is 1, that means there is an overflow. So this is the SSP OV. We have another flag, which is the W collision. So what does mean collision? W collision is for write collision detect bit. So this will detect a collision. So if it is 0, there is no collision. But if this flag is 1, that means the SSP buffer is written while it is transmitting the previous word. So here it is a collision. See there, okay? So this is the SSP overflow. We have seen this bit. The CKP, we have seen this bit that permit us to select the mode, and you have the SSP enabled to enable the whole SSP module. Now we need these 4 bits. These 4 bits are very important, because with these 4 bits, we can select the mode of the SPI, we can select the mode of the I2C, and we can select between SPI and I2C. So here we have SSPM0, SSPM1, SSPM2, and SSPM3. So I've seen the SSP enable, the CKP, and these are the 4 bits that we need for the configuration. So if you have 0, 0, 0, that means we have SPI in master mode. And the clock will be the frequency of the oscillator divided by 4. So the clock, that means the clock of the transmission. If we have 0, 0, 1 in these 4 bits, that means we have the master mode, and the clock will be the frequency of oscillator divided by 16. If we have 0, 0, 1, 0, we have master mode, and the clock will be the frequency of the oscillator divided by 64. If we have 0, 0, 1, 1, we have master mode, and the clock will be the output of timer 2 divided by 2. So we can use timer 2 to be the clock for this transmission. Now, if this bit is 1, so 0, 1, 0, 0 or 0, 1, 0, 1, so we have here the slave mode. So you can select between slave and master by using these 4 bits. And for the slave mode, if you have 0, 1, 0, 0, so the clock will be the SCK pin, and the SSP or the chip select pin control will be enabled. But if you have 0, 1, 0, 1, so the clock will be always the SCK pin, and the SS bar pin control will be disabled. So the SS bar can be used as input output pin. Okay, so here we have 4 bits. With 4 bits, so we can have up to 16 combination. Okay, so here we have just the combinations that we need for the SPI. So the other combinations will be for the I2C. Okay, so these are the configurations that we need for the SPI. So we have to select between master mode and slave mode, and we have to select, if you have master mode, we have to select between the clock frequency. It can be the frequency of the oscillator divided by 4, divided by 16, divided by 64, or it can be the output of timer. Okay, so we have seen that if you send something, so after making the configuration of the SSP status, the SSP control 1, we have to put your data into the SSP buffer. And for the master, this will initiate the transfer by making a rotation of the data. Okay, so you can see that the data here is traveling within a loop. Okay, so if the value, if you put here any value, it will be transmitted to the slave, and the value that we have in the slave will be transmitted to the master. So the data here travel within a loop. Any question about this?
No,
So
clear, Doctor.
Okay, so here we have an example. So here SPI in master mode. So here the SSPM, the bits from bit 0 till bit 3. So here we have the value 00XX. 00, that means if we return back, so 00, and you have the master mode. So if you have here 00 master mode. If you have 01, that means you have SPI in slave mode. Okay, that's why here we have 00XX. Okay, then for the slave, here we have 010X. So 01, that means we have slave mode. So the first device is configured as a master. The second device is configured as slave. So let's see an example. We have to use two PIC 18 4580. One is set as a master, the other as slave. So how does it work, this connection? So the master has a counter that runs inside of it and provides sample data for sending to the SPI link. That means you have a counter within the first microcontroller, and you have just to send the value of this counter to the second device. So the data is sent by the SPI, and the slave has to display it. So the slave will receive the data by using the SPI mode and will display the result by using port B. So as has been mentioned, the slave will also send the data to the master, because we have seen that the data transfer in loop. But in this case, the data is not used by the master, because the master has to send the data, and the master doesn't need anything from the slave. So if you receive something, we have just to ignore it. That's why here the master will discard this data. So we send something, we have to receive something. If we receive something from the slave, in that case, we don't need it, so we have just to discard it. But we have to read it. Why we have to read it? Because if you read the data, you will clear the flag. Okay, so when the slave obtains the data, it will be displayed on LEDs. So here we have the master, the device number 1. It is connected to the slave, which is the device number 2. So the master is connected to the slave. Okay, so the master has a counter here. The counter will be incremented automatically. We have to read the value of the counter and send it using the SPI protocol. How to send it? We have just to read the value from the counter and move it to the SSP buffer. Is there any question? Shabab, after 10 minutes, this will end the lecture, so please use the same link, okay? Now, the slave has to receive the data. How to receive the data? So if the flag becomes 1, so I've seen that we have the flag, BF. So if the flag is 1, that means there is a data. The slave received the data. So the slave has to receive, how to read this data and send it to port B. So the main task here is reading the data from the SSP buffer also, and move it to port B, and you have 8 LEDs connected to port B. So the master has to send the data, and you have to read the value from the counter and send it to the SSP buffer. And for the slave, it has to read the data from the SSP buffer and send it to port B. So here you can see that we have the clock. It is connected to the clock, so the master has to generate the clock signal. And here we are using the pin RA2 as ship select. Okay, so if you want to initiate the transfer, first of all, we have to put RA2 to the ground. We have to make RA2 as 0. We have to send the data. We have to move it from the counter to the buffer. And once we have done, we have to put this RA2 the high state so that we deselect the state. So the RA2 on the master is used as input-output line to talk to the slave select line. So the master can use any standard input-output line to communicate with the SS to the ship select pin, okay? So here we use it just RA2. It is an arbitrary choice. So we can select any bit, any input-output bit. So let's see the flow chart of the master. Okay, so we need a program for the master and program for the slave. So this is the flow chart of the master. So we have to start. We have to make the configuration, set up the variables, set up the ports. We have to make the configuration of the SPI. Now we have to load the SSP buffer with the data to send. So the data to send is the value of our counter. Okay, so if you load the data to the SSP buffer, if you move the data to the SSP buffer, this will initiate the transfer. Now we have to here keep looping, waiting for the flag to be 1. So did the SPI transfer complete or not? So as long as the flag is 0, we have to keep looping here. Once the transfer is completed, the flag will be 1. That means we sent the data. At the same time, we received data from the slave. So we have to read and discard this data because we don't need to receive anything from the slave. So we have to read it just to clear the buffer and then discard it. Then we have to increment our counter and return back to load the value again to the SSP buffer. Any question about this? Okay, so this is the program. It is very simple. So here we have just counter 0 at the address 20, the delay 0 at the address 21, and the delay 1 at the address 22. So we need these 3 variables to generate the delay. Okay. Now we have define here. We are using define CS port A, 2. So this define. So it is a directive, the define. So what does it do? It will define the CS as port A, 2. So anytime we write CS, the assembler will change it by port A, 2. Okay, now we have to set up the SPI. So first of all, we have clear F, trace A, set port A, all output. So we need just the pin RA2. Okay, but here they are making the whole port A as output. Now we have to disable the AD conversion. So we have to load this value to the atcon 1. Now, for the master, the clock should be input or output. For the master.
Output. Input, doctor.
So it is an output. So the clock, which is RC3, should be 0 because it is an output. The SDO, which is the RC5, it is output, okay? And the SDI, which is the RC4, so the RC4 should be input. So here, the RC4 is input, the rest are outputs. Okay, so this is the value of 3C. Then we have to make the configuration of the SSP status and the SSP control 1. Now, if you want to start sending the data, so here we just selected the for the SSP status, the SPI will be at the middle of the output time sampling. Okay, so here we just made the configuration of the SMP bit. For the SSP control, we selected the mode 1, the SPI in master mode, and we selected the SPI clock source to be the frequency of the oscillator divided by 16. And we enabled the SSP module. You will get this value of the SSP control 1. Now, if you want to start sending something, we have to make RA2 as 0. So here, bit clear file, CS, yani bit clear file port A, 0. Okay. Then we have to read the data from the counter and send it to the SSP buffer. We have move FF, counter 0, SSP buffer. And then we have to check the flag continuously. We have to wait for the flag to be 1. So we'll keep looping here, Once the flag becomes 1, yani the data already transmitted. And at the same time, we received something from the slave. We have just to read it and discard it. So how to read the data? Same thing, we can use move F or move FF. So move F, the SSP buffer, comma W. So just we read the value from the SSP buffer, but we don't need it. We have done with the transfer, we have to set the pin R8. Okay, then we have to increment our counter and wait for a certain delay, and then we have to return back again to send. We have to return back again. So the idea is the same. We have to make the configuration of the SSP status SSP control, put your data to the SSP buffer, and then wait for the flag to be 1 before sending the next data. Any question about this? So this is the program of the master. So let's see the slave. So the slave has to read the data and send it to port B. So when do we have to need to read the data? We have to read the data if the flag is 1. So we have start, set up the variables, configuration of the SPI. We have to load the SSP buffer with the data to send. So here we don't have to load anything because we have just to receive. So the receiver has just to check the flag continuously. Okay. So if the flag becomes 1, that means the transfer completed. That means we have a data received. We have to read this data from the SPI. That means we have to read the data from the SSP buffer. And then we have to display it to port B, and you have to use move FF, SSP buffer, comma, port B. And then we have to return back to check the flag again. This is for the slave. So here we have bit set file trace A, 5. So slave select. So here we selected the SS pin of the SPI. We have to disable the ADC, analog to digital converter. We are sending the data to port B, so we have clear F trace B to make the whole port B as output. Okay, so from trace C, so here we have slave. So for the slave, the clock should be input or output? For the slave, input. So the clock here is input. The SDI is input. And SDO is output. The rest will be zeros. We don't need that. So this is the value of 3C. Now we have to make the value of the SSP status the same value that we have seen previously. So we have the SPI at the middle of the output time sampling. And now for the SSP control, we have to select the same mode, mode 1. Okay. Now we have to select SPI in slave mode, not in master mode. So we have to enable the SS, which is the ship select pin, and we have to enable the SSP enable bit. SSP EN should be also 1. This will give you the value of the SSP control 1. Now we have done with the configuration. We have to check the flag, and it